Hello, hello.
Hello.
How's everyone doing?
I'm doing well.
I'm actually expecting more people to be here. I don't know. Let's see.
I'm from the other section, but I joined earlier.
Yeah, that's totally fine. That's what I meant. I want the first section to be recitation where I talk about things, and then the second one to be the office hours. So like you guys can ask questions, and then I will be like answering them. So that's what I feel like. Okay, let me see. I think some people are in the waiting room. Okay.
Could you repeat what you just said? So
Yeah, I think someone are in the waiting room of this.
okay.
Okay, only 23. Okay. Nevertheless, like I'll start the recitation here. This is recorded, so just let you guys know. Something interesting I want to share. I think most of you might just be using Windows. So interesting thing we do is you can go to Microsoft Store and then Google Linux. Okay, let me share screen. Okay, just you can search store. You can just follow what I did, and then just Google Linux. The first one you got, and you can click install. Or get whatever that is. Okay, this is already installed for me, so I'll just show you. You can do it while I was just sharing now. You can just get it. Once you get that, like you can launch and you get your terminal. Okay, and then you can, once you've done that, type in G++, see what it does. If it gives you an error, like not like mine, because I usually have to have some input, this usually do the compiling thing for you. So it will tell you an error, and then it will probably say GCC missing, G++ missing. This is a C++ compiler. They'll probably say missing, and then I think they might give you some instructions to install it, like sudo apt whatever. Just copy that line and then press enter. Or you can Google it, see how you can install G++. It should be just one line. You just get it from somewhere and copy and pass it, and then you will have G++ installed. Okay, this is my interesting way of installing C compiler. And then something you guys want to keep in mind. So the file system is like the exact same thing from your computer, but you just have to add like m/mnt. Okay, like let's say I want to, so this is my desktop, okay, D desktop and ENEE350 and 2021 spring, okay. Let's say I want to get into this folder, how should I do it? And then my VASP 2.3 is in here. Okay, let me use another example.
Can I ask a
Go ahead.
question?
Yeah, go ahead.
Where did you download what did you download in order to run this program?
You mean VASP?
Yeah.
I think it should be, okay, let me take a look. It should be on Elms, files. Let me search for it. It should be VASP machine. Okay, VASP 2.3-1. Like there's a lot of it at the very end. It's in TXT file. Just modify it to .c++.
Is it in the VASP source code?
Yeah, either way, or the very bottom, you have all of it. Yeah, you can use VASP source code, but this one doesn't have 1.0. Oh yeah, it has 1.0. Just use that. The main C++, just get that.
1.0. Okay.
Okay, let me just do that instead. Why not? Okay, I'm downloading it as well.
Can you show us? Can you share your screen or something? Okay, I'm in there.
Okay, files,
Uh-huh.
VASP source code, VASP 1.1, 1.0, I'm sorry. Then main C++. Let's see, let's say I put in here. Okay. The other folder. Okay, this one, the main I downloaded, you can name it differently, it doesn't matter. Once you have this, let's say let's say I want to enter this folder. The first thing you do, so you check it here, you know, it's in D desktop ENEE350 2021 spring, okay, and then you enter that info, but with MNT in the front, and then like the D or C or whatever drive you're in is going to be in lowercase. You just enter it, and then you can tap to have it completely itself. Okay, that's it. And then you're in there, and you use G++ -O, whatever you want to call it. This is the first thing. Okay. Say I call it VASP1.exe. I think you don't have to add .exe. It doesn't really matter. And then this is main.cpp. Okay. And then after that is done, you're gonna get a file called VASP1.exe. Okay. The way you execute it, you can watch this recording later. The way you do this is /, and then press enter, and you can run it. It's a little bit easier to set up this instead of setting up Visual Studio, but if you have experience with Visual Studio, it's really preferred. Since you're gonna be modifying the C++ code later, you're going to do that. So I think I think in the later phase of this class, or the second or the third homework, I think you're gonna be modifying the VASP, the source code, which is the machine itself, so to speak. Okay. I think someone posting a question in chat, but I can't see it. It would be the best if you want to just interrupt and then just ask the question, because I can't just share and then sort of read the chat at the same time.
So you want us to directly edit the main file in the VESP folder?
That's later. That's later. But there, yeah, you're gonna have to modify the main code.
So like using Vim or something like that?
You can use whatever. I don't care. Like if you are comfortable with CLion, use CLion, anything that you prefer. It doesn't really matter as long as you can run it. But I know there are people who have problem just compiling it, so I'm just giving you an optional way. It doesn't matter. Like, to be honest, it's not even my responsibility to tell you this. It's just like a funky way of doing it. But like, I like to have a Linux terminal inside of Windows. That's just something I do. Does the homework? Yeah, go ahead.
Sorry. So you said that it's easier if we use Visual Studio, right?
Yeah, because later on, if you want to compile it, you're probably going to do that. It's easier to compile like that way. I think a prerequisite for this class is like you have passed like a programming class, like C++ or C or Java or something like that. So I think that's
so is there, like, could you maybe show us how to set it up in Visual Studio?
That's not, like, I can't, like, it's going to take most of my time just doing that. That's why I don't want to do that. There's definitely like YouTube tutorials you can go through. I would strongly encourage you to do that. Sometimes there are minor issues, like, but everyone might have a different issue. Someone might not even have their computer C++ installed, so it's gonna take a longer time. I feel like that's really not necessary.
Okay.
You can just put it in the chat. Why not? Or you can post a link in Piazza. I think that's a very good way. Yekta.
Okay.
If you want to share, I think, yeah, because it's gonna take like a bunch of time, but I can't do any other stuff. But just to help you set up the compiler, which is not something that I wish to do. Okay.
Xiaomin?
Yeah.
Hope I pronounced it right.
Yeah.
Is there any homework? Oh, sorry. Does the homework actually require like VESP programming and like this homework assignment?
No.
Okay, that's nice. Thanks.
So I'm sort of getting ahead of time because I feel like there isn't really much I want to cover for this homework. Unless you guys have specific questions. I want to repeat it. Like I feel like I've covered most of it for the homework one. I'm sort of getting ahead to sort of tell you what's going on, because I think in the class when you just write the code, it's really confusing, and I want to explain some of the parts. That's the main purpose for this recitation. Okay, and then also like let me continue. Like I said, please just speak it out loud because I can't really read chat and share the screen at the same time. Okay, this is the VASP machine. So once you compile it, you run it like what I did here. And let me Control C again. So whenever you're running it, whichever platform, or Visual Studio or C Line, whichever platform, it doesn't matter. Whenever you run it, you'll be like this. Okay, so you will say, okay, you can just follow the lines here, enter a program. Okay, you want to enter a program, right? And then it tells you where do you start your code. Okay, let me say I want to start with 020. It says 3-digit hex number. Okay, I'll come back to this later. Just follow it through here. So enter the instructions 0 using a 4-digit hex number, or type -L to enter instruction. So you want to do this. But this might not be correct. So in the other ones, they might give you an option so you can load up your whole script, and then you're gonna be encountering a problem like that. How do I enter the script? How do I write my program, right? So let me just end it here. So you probably can run this one after you write a program. So this is something I want to do today. I can potentially send this to you guys. This is something I used in this class to write code. If you have a question, please interrupt. Please feel free to interrupt.
Is this the same thing that Professor went over in class last lecture?
It's similar. It's just a way I write it, and then I feel like it could be helpful to you guys.
Okay.
So it's a very I think he's not very clear about one thing. So in real computers, this should be called memories. So register will have its own space. Let's say here, these lines are registers, and let's put in this in red. And this line, this whole stuff, we're gonna call this, let's say the green stuff represent the memory. So there will be physically in different spaces. So they're separate. So if these are the registers that you can use, let's say register A, register B, accumulator, and MAR, MDR, the stuff we talked about, those will be allocated in a different space. Those will not be in the same space as we're sort of thinking of it like here. Now, like just a different case or a special case scenario, we say, okay, the registers are in the same space of the memory. So we assign it the same way we assign the addresses for the memory. Are you guys clear what we're talking about? So in real life, registers should not be in the same space of memory. And then the naming system will be totally different. Let's say when you're referring them, you might have two ways of naming system. Let's say the memory will be for, let's say, 16 bits. Okay, 2 to the 16 will be like a lot of space. Okay, I just put it that way. And then the register will only have 2 to the 6, 64. Like if you have questions, feel free to interrupt. Yeah.
Yeah, I have a quick question. So when we went through the diagram like we did in class, is it kind of like that address in memory is a pointer to the register?
You mean the point counter, PC?
No. So you said like the register is actually separate from the memory.
Yeah.
Even though we kind of have that blurred line. So could we consider like address 0x000 as a pointer to the actual register A?
Yeah, you can think of it that way, yes. Or yeah, you can think of it that way. So like this one, like it's just a naming system, or you can think of it that way. This is a naming system. This might not reside in the same space physically. So usually like the naming system will be different as well, and they're still in a different system. But when you're writing them, we are writing the code, you see the naming system like here, they're gonna ask where does your code start? And then the beginning of this address, or you can beginning of the memory, whatever you prefer to think about it, will be the registers that you can use. Everyone understand?
Actually, I was gonna ask like the difference between address and memory. So an address points to the register stored in the computer's memory, I guess.
Like, to be honest, like in real life, you can just call that register. Let's say I want register A, you can call register A. There isn't like an address for that, but here in our case, you use this address to call register A.
Right. And then what does the memory do?
So like I said, it's a special case. Like this is how this class is designed. Usually this is different. But here in this space where you do the programming, that reside in the same space. I'm telling you a difference now. That's the whole point I want to make.
Okay. I kind of get it. So the address is basically you store the register, and then the memory
Yeah.
is just there.
It's just for this class, you can think about it that way.
Fine.
In real life,
Yes.
like they're in different space. Okay. And then later on, we're gonna be talking about like self-modifying code. Okay, which self-modifying means the code is going to modify itself. And then based on that, you have a loop. So you assign so you know the addresses of these spaces, and then we write the code, right? And then you can come back to refer this address and then change the content of it. Okay, he's gonna talk about auxiliary move. It's like you go back and change your index. Let's say when you write a for loop, right? And then the I is gonna be keep changing it. How do you change it? You change it through an auxiliary move where you're modifying whatever this code was all about. Okay. And then, okay, I'm gonna come back and they say, when you enter if you remember, when we first talked about this program, we're gonna say, okay, where enter the program start address, right? Why 020? Because usually you want 32 registers here in our case. 020 is like the 33 address for the coming ones. You can, however, start it at any other line. It doesn't matter, like it's not restricted. Okay, you can start it like later on. Let's say I want to start it with hex 0030. I want to start here. Right, you just have to move all your codes down there, and then fill this gap with I would say with nonsense, with some numbers that doesn't represent any opcode. Let me pause here. Do you guys understand what I'm talking about?
How big does the gap have to be?
It doesn't matter. It's all depending on you. So you can even starting to write code at hex 00FF or 0x0FFF, right? It can be like, that's a huge gap, as you can imagine. But you can do that. It doesn't matter. But it's easier for us to understand or to read the code, since I don't have to scroll all the way down there to see what's in there.
So does there have to be a gap at all?
You need a gap because you need this memory spaces to be registers where you can have direct access to.
Oh, so basically, like all the gaps are where is the stuff in the registers are stored?
Yes.
Okay. Sure. Thanks.
Why do you need to fill them up though? Why can't you just leave them empty?
Because in real life, as you can imagine, there's always something in there, right? You don't have to fill them up, but like you need to let the program know, okay, this is the address of the 32 in decimal, 32 line, a 32nd line, right? That's all you need. Because in theory, unless you're using those spaces, they are never going to be called, so you don't care about what's inside of it. Do you understand?
Yeah, thank you.
Yeah, so that's why you enter something, or like usually something it doesn't make any sense, okay? Because you will return an error. In some cases, like let's say you made a mistake in the code, you have to visit this space, but you know you don't want to use this space. It's like your code has nothing to do with it. So it's going to return you an error. Okay, says this code doesn't work. Give you some opcode that doesn't make sense. So you know that's what's going on. Okay. Everyone good? Any feedback? Come on.
So is basically the setup now is that these are like the translation of the for loop code that's stored at the bottom, and then we should is that correct?
I'm not necessarily talking about for loop. I'm talking about how to program in VASP, and then how are the data storage and the register storage and the code was stored.
So then what is the code at the bottom? What is that code from? Is this the instruction sets for load,
yeah, like
move, things like?
I'm going to do a little example. I'm going to show you like how to sort of write it, and then maybe we can let's say translate it into a program that's VASP readable. So it's like VASP program.
Okay.
So are we saying that at every location of memory it's storing 16 bits?
Yes.
Okay. And another quick question, and I might be, if this is too off track, you know, it's fine.
Yeah, go ahead. It's fine.
You don't have to go through it. So when we're talking about instructions, when we're talking about like the load instruction, for example, the hex code, if you're trying to load into a register A, would be 2000. And I was kind of confused about that because the actual opcode for load is 010. So if you're in a 16-bit architecture, 010 would correspond to like those 4 bits in the hex code would correspond to 0100, which would be 4 and not 2. So I was kind of curious how that encoding works.
I think it depends. I think in this one, let me double check. This one typical example.
Oh, so that's a 4-bit opcode.
Yeah, I think it's 4-bit opcode. So I think it depends. So like, yeah, let's say when you're a 3-bit opcode and then this space limited, and you know the operand is going to be 13 bits, and then that's not going to be a 2, right? But if it's 4-bit opcode, it's going to be a 2, as you can imagine.
Okay, so so when you're actually programming the VESP machine, like the C++ code, and you are using the load instruction, you're still using a 2. So are we actually dealing with 4-bit opcodes?
Yes, I think so. Yes.
So is that last, I guess, is that first 0 just unused for right now for our purpose?
Yes.
Oh, okay, so we have an empty 0. Okay, I understand.
Yes. Yep.
So the highest opcode you can have is still a 7,
yes,
which would correspond to the 8th instruction, and then you're kind of just wasting, not wasting, but just not using
You're just not using it. Yeah, you can potentially add more opcode into it. You can say that I have defined this, so you can edit the main.cpp file, as we can imagine, to add more functions to it, right?
Okay.
So that's one of your homework in your future work.
Okay.
Okay. Any more questions? This is confusing, and I'm trying to get you ahead of time, so whenever we're in the class, you understand what was going on. So the professor is going to write something on the left hand, like that says address. Okay, where like he's usually going to start with, let's say, hex number 0020. Okay, and then the right hand side is going to be the code. Okay, and then in this case, let's say this is what we want to do. We want to calculate this number, okay? And then we save it back to this address. So memory 20. Okay, what we do, we have to move whatever was in a register 14 to A. So like I was doing here, usually you want to write up your logic first, and then you write the code. You want to know what you want to do first. You want to write something up like this first, because you can't add 3 numbers or do 3 things at the same time. Okay, you can do only one addition as like the add instructions gives you, unless there's like given function, let's say add 3. Let's say add 3 that add register A and B and C.
Question.
Yeah, go ahead.
How do you know? So in column C, you wrote 3.
Column
now-
C. Yeah,
Yes. You wrote 3 indicates as move.
yeah, that was given. Usually this is given. You can take a look at the lecture by week or in his notes. The opcode of what they're doing is usually given. Let me just go through here. Why not?
And then 2 is load. Is that correct?
Yeah. So 3 is move. It's like moving from one address to the other. And then 2, you're talking about 2. 2 is usually loading a number to a place. Let's say, so this is very helpful. So I would strongly encourage you to go through the lecture notes by week. I think it's week 2 or week 1. All right. 3. Okay, this is what it does.
So it could change depending on our instructions. Is that correct? So for example, in the homework, we don't have the instructions in the same order as it's listed here.
I think the way you drew it doesn't matter. It doesn't really matter.
So it could change.
Yeah, like
Yeah.
you can. So I think in the homework itself, it doesn't really tell you, okay, which opcode has to do what, right? You can put it in any other order. It doesn't matter. I'm
Oh,
not restricting you to, let's say, opcode 010 does what. No, I'm not restricting you. It just tells you to design a controller to control 18 bits or 18 functions, right?
is this a table of? One of the questions asks about writing a table. Is that what it looks like?
I'm not sure which one. I would say, could you ask those questions during the office hours?
Okay,
So I think we're sort of going a little off track.
sure.
Okay, like I'm just saying, okay, so this is how you find out what does what. So 3 here represents a move. So move that address here. That's why I put a 3 here. Okay. 000 is a destination. Okay, which in here represents register A.
Okay.
Okay. So let me put it another way. Memory address of 000 represents register A, which is weird because in real life it never happens, but that's the case here.
Salman,
Yeah.
what exactly are you trying to move in the register A?
So whatever was in memory 14.
So memory location 14?
Yes, memory location 14. So this is the 14 was in hex here. So number represents actually in 4 bits. 4 bits hex number. So each 1 bit represents a hex bit.
Well,
So 14 is 20 here.
okay, I don't see anything though in memory address 20.
Like because we never defined whatever was in there. We can define, let's say we can define the number, but we don't care.
Does it have to be like 14 or does it have to be a specific number?
Let me my bad. Let me just read through this. This is from previous homeworks.
Right.
So write a VASP1 program to carry out the following computation and verify that your program worked. When you say
Okay.
verify, and then
Right.
you enter the number there.
Yeah.
Let's say 20. Let's say this is equal to 1. This is equal to 2. This is equal to 3. And then you want to calculate out and then eventually this is changed to, let's say, 2 times 1.
Oh, I
plus-
got you. You got to
plus
convert
2
that to
minus 3.
hexadecimal.
It should be equal to 1. And here it says, okay, these numbers are in decimals.
Yeah.
And then when you go back here, everything should be in hex number.
Right.
Like the ones here, like the ones we talk about here, and then even like the mem 14 here.
Oh, I got you.
Yeah,
So
that was my
basically-
bad. I should explain first.
20 in decimals, 14 in hex. Okay, that makes
Yeah.
more sense.
So when you verify it, so like it says when you verify it, so let's say you enter number 1, 2, 3, and then when you run the program, this should, okay, this is a bad example. This should change back to 1. But okay, let's say 2, 2, 3, 2 times 2 minus 3. Eventually this should be equal to 3 after the operation was done, after you run the code.
Right.
Okay.
Wait, because it's 2 times 2 plus
Plus
2
two.
minus 3.
Yeah. So that's after you're done, you can check within that memory address what's the number is this.
Okay, that makes
Okay.
sense. Thanks.
So first, so when you do addition, so you need to refer back to here. Let's say when you do add, you add whatever was in register A to whatever was in register B, and then save it back to A. Okay, so you can add only 2 things, and then the result's gonna save back to A. Okay, put that in mind. And then when you do complement, you can only complement register A because like you're very limited to what you can do. It's not your, oh, I'm coming up with a new function. No, your functions are given. You're just putting them all together to make it work. That's what it does. Okay. And then let's come back here. And then first step, you put things in A, and then as you can imagine, you put things in B. Should be 1. And then you want to 2 times register A. Oh, let's say, how do I do 2 times register A? Wait, I'm sorry. So you can't do 2 times anything because there's no function here. So what you do is you add A to A. You add the memory 14 to memory 14 itself to get 2 times A. Okay. Okay, I'm gonna go into a little bit faster here. And then as you can imagine, now whatever was in A should be 2 times of memory 20 or 14 here in hex. Okay, and then what we do is we load up the number of memory 15, which is this one. We load it up.
I'm confused. In the code you're implementing, it says memory 20, but you're accessing memory for, or you're
Yeah. So these numbers 20 here are in decimals.
Oh, okay. So that's 14 in hex, right? Okay.
Yeah. And then the numbers 14 here is in hex.
Okay, got it. Thanks.
All right, and then you load this up into B. Is there any question? I think I heard something.
You loaded or you moved it?
What?
You loaded or you moved it?
So you move the whole thing there. What I was supposed to in here, you move that into here.
Also, when you're adding A to A, how does that work? Because you only put 0, 0, 0.
No, I add A to B. So I load the same number to A. I load the same number to B, right? And then what this does, this is addition of A equals to A plus B.
Okay.
So now this one is A equals to mem.
I got it.
Yeah.
When you're using the opcode for like add or complement, all that matters is the opcode. Whatever you put after just doesn't matter, right?
Yeah.
It changed.
So like this one, let's say if you put, you can try it out. I would say if you change to 0999, it doesn't matter.
Okay.
You can try it out. So I would say play around with it. Or if you are very super dedicated, go through the main.cpp file. You will see, oh, that's how he does it.
Got it.
Wait, so if you put 999, that would still add it?
Yeah, so because like you only read like this one, like for add, it doesn't matter what the operand is. There's no operand here. You only care about the opcode. Unless the opcode tells you, okay, I want to, let's say, move here. So these numbers will matter.
Okay, so the first one only. Okay. Also, B equals memory 14. It accidentally changed it to 15.
No. Oh yeah. Yeah, I was like talking and then typing. Yeah, not bad. Okay, and then once you add it up, register A would be 2 times memory 14.
Wait, so when you're doing the addition, right? I see that you gave the address for register. So when you say add, right? How does it know which register to add and where to store the
That's
added.
that's predefined.
So add will always add registers A and B. Okay, so no
Yeah,
matter what. Okay.
that's yeah. And then for complement, you always complement A no matter what. You won't complement B. It
I
doesn't
see.
care about anything else.
I see. I see.
Let's say if you want to do complement, you have to always move things to A first,
Mhm.
and then do the complement. We'll talk about that in a bit.
Oh, okay.
That's why like it's not easy to just write the code in here because like you have to think about how to move stuff, and it manages it. Okay, now what we do, so you wanted to add this part, right? We have 2A now. We have this part, right? Now we want this part, so that's what we do. Okay. What's the next? We want to add them, right? Well, what's this line?
0, 0, 0.
Yeah, you can say 0x, x, x. It doesn't matter what you put in there.
Question.
But yeah, but go ahead.
So for the previous part, when we say memory 15 goes to register B, so we say move memory 15. How does it say where does it move to? Like where do we
Here.
indicate the location?
Here,
Oh, okay.
look at this.
I get it.
Memory address of 000 represents register A. So it's stupid. That's why I put in like some time to like sort of explain. In theory, this should be in two different places, but somehow they're in the same place. And then you call memory 0, memory of address 0, you call it register A, which is stupid. Okay, but it's just a way of exercising it.
I got it. Okay.
So like the opcode on the top, that's like, so that's like the instruction, and then right next to it is like the address has to be moved to.
Yeah.
And then 0014 is where memory 14 is stored.
Yeah.
So it
14
moves from
basically
bottom to
gives you-
top.
Sorry?
It kind of moves like from bottom to top, you could say. Like
Yeah. Yeah.
Okay. Thanks. That makes a bit more. Why do you have the 3001?
That's like move to the to the.
So
Oh, it's moving to memory location 1.
and then
right.
and then that's what you call B.
So 0 is A,
Okay.
and 1 is B.
Yes.
Okay.
And then later on you can define, so you're gonna know, okay, index, right? I call index IDX, okay. You can call this index, call this accumulator, call this sum, call this whatever. It doesn't matter, whatever you want to call it, right? You just have to put in mind when you're calling memory address 004, this is a sum. You're gonna be doing sum for sure, okay? You're gonna know how you're gonna do that, okay? What about this line then? How do we add this up? 000, right?
So we wanna.
Go ahead. I don't know who's talking. Two of you. Okay, if no questions, I'll keep going. Okay. Now, since like, if you want to get a negative of something, or you want to do minus, it's complicated. It's a little bit more complicated. First, you have to do the complement and then do +1. That's something about computer architecture. So I'll just say it, like put it this way. So it's just how you do it. Depending on the number system as well. But in here, when you want to get a negative of something, since there's no minus, so we can only do complement. Okay. When you want to get the negative of something, you want to do the complement and then do +1. Okay, just put that in mind. And then we have this number. There's no way we can sort of put this in register A and B and still getting the negative of this. So that's why I store the value of what we just computed into memory 3. So this is like, we can call this 10. It doesn't matter how you name it, but you just have to know what was going on. Okay. what this number should be?
0,
All zeros.
0, 0, 1.
Why was it? Why was all zeros? Isn't it an add? Why was it all zeros?
You're taking from register A and you're putting
Exactly.
into 3.
So the number here, when you're getting out, is in register A, right? And then you want to move whatever in register A to this here. That's what it was doing. When you're doing move, the second line represent where it is going to go. Okay?
Is it always like 2? Like, could we have 3 rows for one instruction?
It's just how it was designed in this machine. In the machine you designed, it could take 3 lines, but let's say you want to add 3 registers and save the sums to, let's say, right? It could take 3 lines. If you design it that way, you enforce it. Let's say I call this opcode 9 or A, whatever. This is something you design, you could. But this is the case. It was given. Okay, that's it. All right. And then what you do is you load this number up. Okay, I'm just gonna do it a little bit faster here since I think we're a little bit running out of time. I want to accomplish it before the session ends. And then you want to do the complement. How do we do it? Can someone tell me?
You just do 1 and then any destination.
Exactly. Like it can be XXX, but to be convenient, we like usually XXX, I would just put 0 here. It doesn't matter, whatever you want it to be. How do we set it to 1? I think this is something we talked about in class.
Do you use load? So like 2 0 0 1, and then the next line 0 0 0 1.
Exactly. Okay, let's say I'm just an example. I don't want it to be 1. I want it to be 6. How do we load it?
Next line would be 0
0
0
0
0 6.
All right.
0, 0, 6.
All right. So I think everyone is clear of what's going on. Cool. And then we want to get the 2's complement.
So 3.
First, want to make the location of register A, right? So something like whatever the move opcode is, I don't remember, and then whatever register A is. So like, yeah, 3000. I think that's the move opcode.
Yeah, you save that to register A.
Wouldn't it just be 0 0 0 0?
Here.
Because you just want to add
Exactly.
A and B
This
together.
is something I talked about here. So when you want to get a negative, you complement and then +1. We loaded 1 at B. Okay, so this is exactly what you did. Or what we are going to do. We just added here. I have to make it faster a bit. Okay, I come back, or we can ask questions in the office hours. I want to finish this part, and then what we do here. We want to add them up, right?
You move, you do like 3 0 0 1, and then next line would be 0 0 0 3, wherever we stored the last.
Exactly. So as you can always, so we're putting the result of this part, right? This front part into memory 3, right? We can also access that, right? We can always access it like what we did. So what we're doing here, we're moving that back to B. Why we move back to B? Because you can only add register A and B and store it back to A. That's the only reason that we're doing this. We can't just add register B to register temp or register A to register temp. So we can't add this to address because there's no such function that does that. We can only add these 2 things. And then first we get the negative. We get this part in here in register A, right? We just have to load this back to B so we can add them up to get our results. So what do we do here?
All zeros.
All zeros. We just add them up, right? You're getting the negative of VASP. here, you just want to add the two parts. Okay, I think this is pretty clear here. So you just add the two parts. You're adding this negative part. Okay, and then the final thing we do, move the result back to memory location 20 in decimal or 14 in hats. Okay, so we have the result, and we'll move it back. How do we move it back? Someone else.
300.
300.
We are moving it to
What was the destination we want to move back to?
14.
to A.
14. So
Yeah.
it's going to be 14 here. Okay. So what was here? Or what is going to be here?
Source.
0003.
003.
Oh, sorry, 001 because it's in register A, right?
Exactly. So the result we get, whatever you're gonna add, is gonna come back to memory 0. Okay, this is stupid. Let me say this again. This is stupid. So this is gonna be memory 0, and then you move this whole thing, which is memory 0, which represents memory 0 or register A. I don't know if there's a better way I can describe this. Yeah, put it like this. Okay, and then we're done. Problem solved. This is one of the problems from the previous homeworks. Okay, we're done. That's all about the part. And then, okay, usually I would say you have to have a halt, because in theory, when you're in the memory space, it's never going to be empty. Okay, the number is there. Like even if we leave it empty here, but as you can imagine, there's always going to be a state of 0 and 1 for any of the resistors or transistors. Okay, there's always going to be a state there. So so what we do is we put a halt. Okay, I'm gonna come back here a little bit, a tiny little bit. We just put a halt there. Tell you, okay, this is the end of our program. Okay. So we do, as you can imagine, this can be 7xxx. It doesn't matter, whatever you want to put it there. But to be neat, put 7000 there. Okay.
What does halt do?
Suppose basically tell you, okay, this is the end of our program. We should not execute.
It's just end.
Yeah. Okay. And then this space can be used for you to load numbers like what I talked about. Let's say 14, I want it to be 3, 2, 3, 2. And then when you are entering numbers, you have to put in the zeros in the front as well. Right? And those blanket space, put in like something that doesn't make sense, like A's. Okay, since A is not an opcode here, so fill them up with A's.
Do we have to do this because the program tries to start
Yes.
executing from position 0?
Yes.
Okay.
You have to do all this.
And then it just
Can
goes
you-
down until it reaches an opcode
Yeah.
that can actually execute.
Yeah.
But can you, on the VES machine, can you specify where the program begins?
Yes. You
So
can
when
specify
you're-
but when you're so it because like it matters which address of this line is. Yeah, keep going.
Right, but on the, like when you're running the VESP, you can say, like, for example, you know, if you want the program to start at 0020, you can say that, and then can you just do whatever you want with those with the memory before that?
Yeah. So this is basically what I'm saying. Like I'm doing whatever I want here. Usually it doesn't matter, but when when there's an error in your code, like this will return an error, so you know there's something wrong. Or like, what if this is, let's say this is 000 here, like you misread it as an add, and then it gives you back a incorrect result.
Oh, but in theory that shouldn't happen even if you have 000.
Yeah. Yeah.
because-
In
So that would
theory,
just
it
be
doesn't matter. In theory, it doesn't matter because you're never accessing that memory.
Okay, that would just be if for whatever reason the machine goes to the wrong place in memory and sees this opcode. Okay, so
Exactly.
it shouldn't happen.
exactly.
Yeah, and they can be modified after that. Is that correct?
Yeah, they can be modified. So this is something else I want to talk about. When you are loading the numbers, I want, let's say, memory in memory location 14, I want it to be 3. This is like constant. So memory 15 would be 3, memory 16 would be 2. We can load it up this way. All right. Or you can just put the numbers there, right? As you can imagine, like when you are initializing the state of the machine to say, okay, that I want memory 14 to be 3. So you just put a number here like this. All right. Or you can do it the way like this. Maybe you're gonna going to load up numbers 2001, 0001. Like this is for register B, but like for the rest is the same. If you want to load up memory 14, how do you do it? Load up 14 S3, how do you do it? Use the ODA as well, right? It's going to be the same thing. All right. Yeah, 250. Okay. I think that's all I want to talk about for today. It's gonna help you understand when the professor is gonna go through the loop. The loop is very important because it's, let's say, because you're gonna have jump which go back to some memory address, and then you edit the things inside of it. So the address you're going to may be changed. That's the beauty of it.
Which homework question was this that you were doing?
No, I'm just saying, like, later on when you are writing a loop, you're going to modify the code, which means, let's say I execute through the very end of this, right? There's a jump command. You can come back to the front here, some of the line here, and then you can modify it. Let's say you can modify wherever this result goes. I think the professor will talk about it in class, and then this is the beauty of it.
No, I
Of the
wanted
self-modifying machine.
I wanted to know what homework problem was this that you went over. So then they.
Oh, this one. So you're adding this. I think this is recorded as well. This is here. Why don't I just copy it here? I can send this to you guys if you wish to.
Yeah, that'd be nice if you could send it.
Yeah.
Thank you.
And then this is like the way I write the programs for this class. The way I write it. So like I have this, and then you can copy this without format into Word, and then copy it to text, TXT, Notepad, whatever. It doesn't really matter.
Thank you.
Right. That's it for today. Stay for the office hour if you wish to. Otherwise, that's it.
Thank you.
Thank you.
Are you taking a break or should we start asking right now?
You can ask questions. It's fine. I'll be drinking some water at the same time.
So I wasn't really sure what the question means for part C when it says the processor operates on operands in 2 register A and B. How many bits are needed to distinguish between these 2 registers? So like A takes 5 bits, B takes 5 bits.
Give me 1 second. Which part was it? Part C?
Yeah.
Yeah, like exactly what it says. How many bits are needed to distinguish between 2 registers?
Like, what does that mean? To distinguish?
You have 2 things you want to choose. Like how many bits you want to use to choose them.
So like with that.
I can be more clear, I think.
Would we be? Is there like a? Because I remember professor talking about 1 bit that like separates them. And then there's 5 bits.
Okay. Let me put it the other way. You have meal plan A and meal plan B you want to choose. Okay, you have a coin. Or you have multiple coins. How many coins would you need to flip them over and then choose one of them?
1.
That's it. Yeah. And then that's the same thing about this problem C, I think.
Like 5 bits?
I think 1 bit. It's exactly okay. I should not be telling you this, to be honest. And then later on, I'm not going to tell you exactly this. I think I couldn't explain this better because you have two registers A and B. You want just use one bit to distinguish them, right? If I think I'm correct.
Yeah, 0 or 1. I mean,
It's
pretty.
it's like how many numbers do you need to tell apart the registers? You need one number to tell apart register A, another number to tell apart register B, and one bit can represent two numbers.
Okay.
Or put it the other way, okay? Register A was in memory 0000, right? Register B was in 0001. Right? How many different bits are there from register A to register B? The memory address, only one, right? So you only need one bit to tell the difference between two of them.
Okay, that makes sense now. Okay.
But I shouldn't be explaining this. I'm basically giving you the solution. I think I did really a pretty good job of explaining it. So I think next time I should just stop it there because my job is not to tell you the answer.
Okay, I don't want the answer. I just wanted to know. I didn't understand what the question is asking.
Yeah, it's too trivial for you to answer, to be honest. But
okay, so does a table of opcodes look like?
It looks like the one I just showed you, like
the one that I was asking. That's okay.
I think and I think they're giving you in the order of. I would say just follow the order. It gives an order of 1 through 18. Just follow the order. Why not? Why would
I had a question about the opcode table too. Like I get, and it wasn't that part. It's the part where it asks for like show like what the operand is going to be or something like that. Like the part after the opcode, right? And that's a part that I mean I feel like that part is up to interpretation, but like the way I have been doing it, right, is I have a table where I have like the name of the function, what opcode it would be. And then like in another column, I'm just writing like what components would it have? Like it would have a destination address, a source address, or like, and like that, that's about it, right? Like
so about that, I only have like three columns. One of them is the opcode, which shows the address. One of them is the instructions, and one of them is the format of like whatever I used.
I think this is what I'm looking for. Like exactly this. Opcode, what it does, and then this operation. Like
so exactly that's exactly what you want for all. Okay.
I think that's exactly what I want. And then tell me like which bits are like this ones, right? Exactly what it does. And then this tells you from which bit to which bit does what. Why would I need this? Like that's exactly what I was looking for.
So we are at liberty to define these, right? Like we don't have to
it's fine.
Like for example, for subtraction, we could forcefully define it to be like subtraction between A and B, right? We don't have to like
you can do A to C, whatever. It's fine. But you have to define it clearly. So that I can
use a subtraction operator, or can we have to like explain like derive a subtraction operator from
no, like you can just explain. It doesn't tell
we can just say like A minus B, or do we have to like okay.
Just say A minus B.
Okay, that sounds good. Okay, so that's what I was confused about, because there's a lot of ways we could go.
That's too detailed. Like I don't want that. But you want to understand the logic of this. I think that's good. That's good enough.
Okay.
So similarly, similarly for that, can we use pipe for or, ampersand for and the XOR symbol for XOR, or do we need to define those as well?
I would say if you can use logic gates.
Yeah, so I can just
use a logic AND gate.
Sure, yeah.
And then there's like XOR gates, or you can use AND gate and the OR gate to design an XOR gate. I think that's from previous classes.
Yeah. Okay.
It doesn't really matter, to be honest. Like the whole purpose was more like fetch, decode, and execute. I think that's more like the meat of it, not how exactly this is happening. Because like in theory you can design it, and then this is not well defined. And like I think someone asked like, is it AND bit by bit AND, or is it AND just A and B? I can't tell because I don't know exactly how this was defined. I think you can define it, right? unless in this problem it clearly states, okay, and is bit y is end, so you have to do something like that. Like otherwise, I think you just do something like.
So for parts like shift to the left and shift to the right, Professor explained what it means, but like he explained it by an example. I'm not so sure how you want us to specifically say the operation in one line.
I would say think about it. I think you can define it like this ways. You can like something like that, or you change it whatever was in IR, or you get what are the bits within that position and then you shift it, or you can just write shift to the left. I think it's fine. It's not the very purpose of this class. The class is about computer architecture. You have to understand how the computer works, like not exactly how this operations does what, because that's something you can define. I can call the operation XYZ and then does something different. And I can design an operation as you were mentioning. Oh, can I use 3 lines? Yes, you can use 3 lines. You can design an operation called add 3. So I want to add 3 registers and then store the values to D instead of A. You can design that. It's just a way of designing.
So about clock cycles, when we're talking about clock cycle, are we talking about like, let's focus on one input. The one input goes into the fetch, so that's one clock cycle, and then it goes through. Let's say it goes through move, so there's another clock cycle until it goes back. That's how we're looking at it.
It basically it depends on the flip-flops.
Okay. Sometimes it only goes through one clock cycle and sometimes it goes through 2.
Yes, and then because so some instructions, they will require even more flip-flops. If you read through the PowerPoint carefully, you will find, okay, some operations will need another flip-flop.
So
like, for example, move.
On the topic of flip-flops and part E, I guess, right? In this where we have to draw all of them. Did you want us to draw it in like the way where like at the very last lecture, or like maybe the one lecture before the last lecture, right? The professor was doing this thing where he was handling multiple inputs with an OR gate and then handling multiple clock cycle inputs with another OR gate, I think, right? But the details doesn't matter. I can always look that up in his notes, right? Do you want that level of detail, or like more, or what he did initially, right? Where instead of doing that, he would write like, oh, here is like where you do after this flip-flop, right? You do like MAR equals to this, right? So
are you talking about the MAR equals PC1 example that he did?
Like, this is the level of detail I want, to be honest. But I don't know how good of a job you guys can do.
My
okay,
God.
So which question does this answer? Because I have this, but I'm not sure which one it actually specifically answers.
This is like how you draw the one hot controller.
I was about to say that's just the part where you go through the decoder, right?
Yeah.
Isn't like,
but like that's the whole part. That's like
because I was under the impression for question E, right, that not only did he want the decoder, right?
Yeah,
but
like,
you know how there's like multiple. That also had the flip-flops before that.
Yeah, because the fetch. Okay, let me just quickly share this. I do not want to, but I think it's fine. It's the previous semester work. So you have the fetch here, and then decode here, right, and then execution from this part. You have everything here, to be honest. And then this is for different instructions, what it does. I want to zoom out.
So this is the one hot flip-flop?
Yeah.
Oh, okay. So could we connect all the flip-flops into one clock?
Yeah, that's what you should do. Every flip-flop should be connected to the same clock.
So like, you see how on the load side we have
like this one, those should be all the same. Those clocks should be all the same.
But can the clocks in the load be connected to the clock in the fetch?
Yes. They should be all the same. All the clocks should be all the same. There's only one clock. There's only one clock.
But as a clock cycle, it counts as 2 clock cycles.
I think that's something I talked about from my last recitation. Every clock is the same. When you say clock cycle, only from the falling edges, it changes,
Yeah.
right? So everything was operating at the same time. So the previous line was, let's say the previous line was decoding, and then this line, you're fetching it. It's happening all the same time. It's not like, oh, I'm only executing decoding, but I'm not fetching, decoding, executing this line. After this was done, I go to the next. No, that's not how it works. Okay, let me see if I can explain it here. Let me share screen. See if I can explain it here. You want to understand this. So let's say this is my first line of code. Okay, you have cycle fetch, decode, execute, right? When this one's going to decode, this is the same clock. Let's say 1 second, 2 seconds, 3 seconds. Okay, when this one's fetched, okay, nothing happened for the second line. But when this one goes to decode, the second line comes in. So this code, let's say register A equal to memory 1. This one's fetched at the same time. And then you decode, execute. And this line kicks in. When this one is executing, you're fetching this one and decode, execute. That's how it looks like. This is your real time. There's only one time or one clock. There's only one.
Okay.
It's like on the falling edges, everything moves forward a bit. Let's say you can consider this 1 second, every second there's a falling edge. For every falling edges, everything moves forward a bit. So if I go from this clock cycle to the next one, there's always something in there. There's always one line of code being decoded. And then like as if in decode or fetch, they might be more using more clock cycles. Let's say the decode will use 2 clock cycles, right? And then you can decode one at a time. So when you fetch this is going to wait. And this is going to look like this. This is going beyond what I should explain, but this is how it looks like. There's always something being fetched, there's always something being decoded, and there's always something being executed.
Okay, I understand that part. But when it talks about clock cycle, it's talking about every falling edge.
Mm-hmm.
Yeah.
Mm-hmm. So here, like the falling edge, let's say, like assume that each 1 second here, there's a falling edge. So the decode is going to happen at the same time, but decoder can only decode one thing at a time. Okay, this is too complicated. Let me just not do that. Just do this. So when the first clock cycle comes in, this is being fetched. Okay. When the second clock cycle comes in, this is going to be decoded, and then this line of code is going to be fetched. This is happening at the same time, at the same clock cycle.
Okay.
At the same falling edges, this is happening at the same time.
Can I ask my question, or Yekta, are you still asking?
No, go ahead.
Oh, okay. Sherman, can you maybe re-explain the typical flip-flops? Because I couldn't really understand like the distinction that Professor Orak was making during lecture.
You mean just flip-flops?
Like,
general,
he was really stressing the difference between the typical flip-flop that he drew at the end of Tuesday's lecture, right? Like he was really stressing that was like different. And so I was just kind of wondering like what made that different than like all of the D flip-flops that he'd drawn before. Like, is the typical
I-
flip-flop, does that refer to all of the gates that he drawn connected to the D flip-flop? Or is it just like that flip-flop itself is just different somehow?
I think the
Does that make
flip-flops
sense?
are the same. The flip-flops are the same. I don't
Okay,
think there's any
so then
different.
typical flip-flop refers to like everything that
Yeah.
was connected to it as well?
Yeah, I would say like how the memory was going to be loaded or write.
Okay,
Like
okay.
when you, I think when he say a typical flip-flop will be like the whole part that's connected to the flip-flop, like you mentioned. Yeah, I think that was a better explanation.
Okay, okay, that makes more sense, thank you.
Or put it another way, how a typical memory is being edited by connecting to a flip-flop.
Okay, and so like all of that stuff is like off of the decoder, right? So then those, that's like typical flip-flop is not the same thing as what's happening in like the fetch, decode, execute steps?
Yeah.
Okay.
Yeah.
So like Professor gave us an example of MAR gets PC as for the typical flip-flop. And then we had like 3 flip-flops that was PC, IR, and MDR. And then they went into the MAR flip-flop.
Mhm.
So when it's talking about flip-flop in register A and the MAR, is it talking about like A going into MAR?
Yeah, because as you can imagine, like this is going to be 16 bits. Let's say 16 bits for now. Okay, we have 16 bits. IR is 16 bits, MDR is 16 bits, and then every other line is connected to the every other line. So each one of this, as you can imagine, is going to be a block, right? That stores things, right? You have 16 blocks of this to accomplish this, right? A typical one of it, or typical one flip-flop of it, will be 1 bit out of 16, and then you should draw it out how this was modified, and then when you're saving this back, okay, so you're like reading it or you're writing it, right? And then I think that's what he meant. Let me say this one more time. This is 16 bits, right? And then when you're drawing it, you're drawing 1 out of 16.
Okay.
You're just giving, so I'm giving one example out of all 16 bits that's connected for these two things, right? Because as you can imagine, in theory, like if you have 16 bits you want to modify, you're gonna have 16 flip-flops, right? But that's way too complicated. I don't want you to draw all 16 bits that's connected to modify, to read or load, right? Let's just save this number back here. In real life, you're gonna have to have those connected with flip-flops, right? I want you to draw 1 out of 16 bits. That's what it meant.
Just thank you.
Yeah.
I think you already answered this, but I just had a quick question about like the typical flip-flop as well, like the register like MAR or no register A in the homework. When we do like sum and like complement, do we have to like craft like those circuits, like those gates, like create like the sum circuit and create like a complement circuit, or can we just write like A plus B goes into like an AND gate? Can we simplify like that?
I would say as detailed as you could. I'm probably not going to take points off, but like as detailed as you could. I probably would not take points off, but as detailed as you could, because it will help you understand.
I mean, yeah, I do understand it. I just think like if I was trying to do like the shift left and shift right, like drawing all of that would be complicated. Versus I can just write. Write A equals
shift left and shift right. You're like connecting, let's say, from first one to the next one, right? And then you, but like it doesn't really make sense to draw all of it.
Right.
Just put a line there. So, okay, so this is what I'm going to do, whatever.
Okay, that's what I figured. It's just during lecture he kind of made it sound like we should do the.
Yeah.
I don't know.
It's fine.
I was just checking with you. Thank you.
As detailed as you could, and then as you sort of the more like important purpose is, like as I mentioned, is like computer architecture.
Right.
How computer was designed, the von Neumann architecture. How was that? And then I think this first homework was a reflection of that, the volunomial architecture. And then you're doing fetch, right? I think that's something I'm looking for: fetch, decode, and execute, and then a decoder, and then some of the code, how you design it. And then let's for move, as you can see in the lecture notes, you're gonna have more flip-flops. So that would need more clock cycle for those instructions. So those are the things I'm looking for as well. But for the simple ones that shift, as you can imagine, like those should be all directly connected. Maybe one flip-flop to tell you, okay, this should go after the one clock cycle, but that's it, right? Then it should be executed right away, and then you go back to the fetch cycle again. So, yeah.
Okay, I think I got it. Thank you.
Yep.
So I know I ask a lot of questions, but like a lot of things still don't make sense to me.
Yeah, it's fine. Keep asking questions.
I'm gonna try and go study them. Like I looked at the slides like you told us to do, and then that helped a lot with the design that I was doing. So I designed the whole, like the example you keep showing us. I have that whole thing. I just wasn't sure which part that's answering, which you told us that's the hot flip-flop part. It's just, I don't know. I just need to go study more. And
I would say make posts on Piazza, and then people might reply as well. And then, do you have like a study group or anyone inside of the class you know of? I usually love to have study groups. Like no matter what class I have, I usually have like a study group. They may not get better grades than I do, but I still want someone that can study with me. So if there's some trivial question in class, there's some things I didn't notice, I'll ask them right away. Because to be honest, a TA like me, I don't really pay attention in class. I don't care about what he talks about in class. I usually jumps in at the very end of the class to sort of like understand some logistic stuff or anything that you want to talk about. But within the class, I don't really pay attention. So
I will be talking to other students in class, but we may still have questions. So I'm just gonna hit you with the email or.
Yeah, I would say Piazza is the best because usually the question you ask, other people have it as well. It's not just you. You can post anonymously, so people don't know it's exactly you, but you post it and then people will see the question. They might have the same concern as well, and then I happen to answer for all of you, not just for you. I think that's a better way. Of course, like I always open up to questions. I think the first thing you want to think about is the bigger picture of this class, and then you go through the details. That's what I usually would do. The bigger picture of the class is volunomous architecture. You want to understand that, and then the fetch, decode, and execute cycle. That's second thing, and then the details. So you want to go through the notes or my lectures or professor's lectures to make sure understand that part.
Okay.
I think when you're initially asking questions, you have like a bigger picture question. You know, you don't understand what was the bigger picture, but now I feel like you're asking like small questions like within the small pictures, right? I think which is better. Like you're definitely learning more. Like make sure you get a bigger picture first. Like this time you're asking like smaller, like very detailed questions, which I really like.
Thanks. It's just you know how the part that you was talking about typical flip-flops and register A and stuff. So like I kept looking at this note that I took during class, and I don't understand how to relate this to register A.
It's like you can like register A is also like a memory space, a physical storage space. I put it that way, not a memory space, a physical storage space, like a memory, but it's faster and you can access it easier. That's it. It has no difference than like a memory. Okay,
I understand that. But how do I draw a flip-flop for it?
You can refer, I think in the lecture notes, let me double check. In the lecture notes, the one I sent you, they have stuff related to A as well. Like you don't necessarily directly, let me just show it right away. You don't necessarily directly like draw a flip-flop for A, but you tell it what this does. To be honest, like this line connected to it, usually let's say add, is going to do something about A. And there's gonna be like a flip-flop of whatever structure for A, but you don't really care the exact details of it. Like this is what you do, you just write it up, that's it. Or
So
for
when-
A of A complement, you don't necessarily care what this one, how this is going to be accomplished, but you just put it there.
Okay, I understand what you're saying, but I still don't understand what the question is saying, because it's saying show the design of a typical flip-flop in register A and the MAR.
So that's like let's like this one. But like when there's like lines that like that, it's A instead. When you're saving or like when you're writing, because like for MAR and A, it's basically saving and writing, right? You're putting MAR into A, you are saving A to MAR. So basically doing this. And then this dots or this lines is going to be different. The function you called, whatever, I think STN, LDA might still hold. But like other things might be different. You can think about it.
Okay, yeah, I need to think about it. Thank you so much. I think I've done the major part, which is designing the hot flip-flop.
Mm-hmm.
And then for the last two parts, it's just me adding 4 more instructions and then upgrading my hot flip-flop design.
Sure.
Okay. I used OrCat for
It's fine. Whatever you want to do, it's fine. You can use hand to draw it, but it's hard to really change it back.
Yeah. And also this is like, I think I know this is the right answer. I just want to double check. When we have a Z flag, that means the negative side of the clock cycle. Like when we have a 0 and 1, 0 and 1. When we say Z flag, that means it's 0.
Yeah, for the let's say usually the first bit, like if you have a number, the first bit represents, I don't know if this is the case in here. The first bit represents 0 or not. If it's a 1, it's a negative number. If it's a 0, it's a 0. So then this is usually the flag. So you usually just get the first bit of the number. So here, the N flag, you can just think of it like if it's a 1, it represents a negative. If it's a 0, it represents a positive or a non-negative.
So
N flag, Z flag is the same. So if it's Z, if you call it a 0 flag, if Z is equal to 1, it means this is a 0. If it's a 0, which means it's a non-0. 1 is like a yes.
Then, you know how when you're doing the jump for positive, and then for jump for positive into
but you don't have a positive, right? You only have a negative and 0. So in which case both of this should be incorrect, right? It should be non-0 and it should be non-negative, right? It should be 0 for N flag and it should be 0 for 0 flag, right? And in that case, you jump. So that means jump positive.
So I would have a Z prime flag and a S flag.
And then you end them together, maybe.
And
what is S? S is select. I don't know why would you need an S flag in this case? What is S?
Yeah, that's so for positive, for jump if positive, I think we only need a Z prime flag. And then for jump if negative, we need a Z flag and an S prime flag.
Where does it tell you to need an S flag? Could you refer to something? I don't know. What is an S flag?
I was thinking S is like, I don't know.
Then why would you need an S flag? I don't know. Me neither. Like, I don't know what's in your mind. You keep talking about S flag. I think you asked that question in Piazza as well. So I was asking you, what is an S flag? You need the flag.
I don't know. When Professor was drawing it, he wrote the Z prime and S prime. And then I asked him, and then he said the same thing that he commented on Plaza. So if I knew what it meant, I wouldn't have asked.
I think N flag and Z flag. N means negative, Z means 0. I think you only need that 2 flags. Positive means non-negative and non-0, right?
Right. So I think that's what S means.
Okay. If you describe it that way, you can say S is a positive flag. You don't need an S flag, just like I said, you don't need an S flag if you have an N flag and a Z flag. You use complement of both flags, and then do an AND gate, and then you give a one signal for positive.
So use S and Z for jump if positive.
I'm not. I never said S. I never said S. I said N and negative, and Z, which is a 0 flag.
Okay, what does the prime mean? That means if the negative becomes positive, if we do N prime.
This means N prime. Okay, this means no complement of N.
Uh-huh.
So non-negative and non-zero, you get a positive, right? And then this whole thing, you can call this whole thing the positive flag, and then you can reflect this using gates. There's a complement gate, and then there is an AND gate. You can just put them together, feed in with N and Z, and you get I don't know. You keep saying S flag, you get an S flag. You're talking about. I never use an S flag.
Okay, let's not use the S flag. So when for jump negative, I'm gonna have an OR gate that has 4 lines, 4 wires going into it. One of them is the jump positive. One of them comes from the flip flop of the.
Wait, you said jump negative. Why are you coming from the jump positive?
I'm gonna ask you about jump negative right now.
Okay.
So we have one wire coming from the decoder that it's jump negative. One wire coming from the flip-flop from the fetch and execution, the 4th flip-flop. And the other 2, since it's negative, it's gonna be Z flag and N flag.
Why would you need a Z flag?
Z means 0.
Yeah. Why would you need a 0 flag?
So we don't.
Aren't you just be good with just N flag?
Yeah.
Why would you need a Z flag? Just think about it before we ask. Like, think about it. What are those flag represents?
So why are we even including the Z for positive?
Because Z is N is negative, right? Non-negative means it can be a 0. Make sure you understand the definition, and then like that's something I said beforehand. Make sure you understand the definition. Really understand it, because you see it right now. You don't even understand. Like M represent negative flag. Non-negative means it still can be a 0.
Okay. Yeah. I'm gonna have to go work on that and edit it. Thank you so much for your help.
Yep.
And I'm sorry if I asked too many questions.
No, it's fine. Like that's my job. Come on. Why you have to be sorry? That's unfair. Like, please don't be sorry.
Okay.
Unless like you want to schedule a meeting on Saturday, please be sorry about it. I don't want it to.
I will not schedule a meeting. I will probably email you.
All right.
Okay. Have a good day.
Yeah, you too.
Bye bye.
All right. Bye bye.